Okay, okay, there she is. And there she is. There's Gabriella. All right, there's Jocelyn. There's Sydney. Awesome. Good morning. Good morning. It's hard to make
Good
eye contact.
morning.
Good morning. Oh, and there was that was a double. I don't even know. Wait, was that Nadine who just said that?
It was me.
It was me. Oh, it was Gabriella. Oh my God. I'm sorry.
Yeah.
Okay, 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 okay. All right, that's a triple right there. Okay. It's so weird to do. I know people. Okay, anyway. All right. And there's Nadine. Thank you. I said Sydney. Did I say Sydney? Maybe I did not say Sydney. There is Norma and Melanie and Effie. Oh, Effie has undergone a transformation. Fascinating. Okay. Very modern. Uh, there's Mohammed. There is, we're going to do this quickly. Oh, and that's Sydney. Yes. Okay. Oh, I did. Okay. Okay. Wait, I'm trying to do this quickly. Nadine, good morning. Good morning. Nadine, Mohammed. Yes. Oh, so, okay. Nadine for the double. Thank you. Mohammed for the double. Thank you. Melanie for the double. Thank you. Jibo, good morning. Thank Effie for the double and the, yes. I mean, what are Cartman's pronoun? All right. Teresa, good morning. Sydney for the double. Good morning. Or the triple. Good morning. Norma for the double. Good morning. Genesis. No one even knows what I mean by that. But anyway, good morning. Genesis. Good morning. Sydney, thank you for the closing the conversational path portal. Lunar for the good morning. Joshua, good morning. Christopher, good morning. And about to be good morning to Chanel. Okay, we're all right. Again, the exams are coming. I promise. I promise. I'm just gonna say that they are actually are happening, and some of them are even but anyway, you're gonna see them soon. I'm sorry, but they're okay. I'm just saying that, and it's not personal. And I know it's okay, but they're coming. They're not forgotten. They're in fact eating at my soul. But back to physics now. Did I say Jocelyn? Good morning for the double. Um, we're getting to that point of the year, and I'm getting feedback from past years. You think it's time for me to be a little bit more efficient in going over things, maybe? So I want to try to cover a little bit more per unit time. So what we're on to what so I want to do. My goal is to sort of last thoughts on sheet on homework that I'll screen share in a minute. Last thoughts on the Newton's Law homework so that I can transition from that to really drilling down on lab 5 that I know you've already done, but you still have to write a report for, and it is a big report. And it is a tricky lab, I think. So really, really the focus of today, are we here? Yes. So really, really the focus of today is I want to give you practice with solving Newton's law problems that involve angles. In other words, I want to see an example or two where forces actually have to be broken up into components, like I keep saying, but we haven't seen an example yet. And I want to get to the specifics of friction because if you put together those two ideas, if you put together an angle and friction, then you really have lab 5, or at least a lot of the subtleties of lab 5. So these two equations on the board right here are the equations that govern friction. They are the new equations. I mean, at least one of them you dealt with or was assumed or something in lab 5, but I've never said anything about them in lecture yet. My goal is to get to these today. Um, but I feel like in order just to stay in order, so that's the goal, is to explain these equations and apply them today. Uh, However, let me do at least one example that involving an angle first, just to stay in order here. Um, so Okay. So a couple, oh, my screen seems to be glitching. Okay, that's I did not know that. Thank you that my screen is glitching. I don't, oh, if it's the, okay, I'll keep an eye out for that. I'm not sure what I can do about that, but noted. If by the screen you mean the whiteboard, the blackboard screen, that, yeah, that may be my hand. I'll be more careful with my hand, but we'll see. But also speaking of hand and handwriting, if ever I say whenever I say N2, like big N with the serifs and Roman numeral two, I mean Newton's second law. Whenever I say N2, I mean like F net equals MA, which is this whole context right now. Um, so what I want to do, so in other words, I want to do one angle problem and I'm going to take it from that homework sheet that we're still going over so that, and then so we can put that homework to bed. So, okay. So quick screen share. Okay. So I'm talking about this homework, right? We're going to finish anything I have to say about this homework, which I think is homework 7. Um, we're going to finish saying today. Again, we didn't do all the details of it. We're doing some big picture stuff. So one thing, see this whole big problem here, this last problem in homework 7. It's involved, if you want to ask me for details of the answers later in an email or something, or if there's maybe there might be old solution sheets like in old YouTubes or whatever. But the one big picture, but I'm not going to go over the whole thing right now, is what I'm saying. I want to say one big picture thing about it. Um, the fact that there's two blocks on the table touching each other. So that constitutes what we sometimes call a system problem. When there's more than one mass acting as a group, that's often called a system problem. What and you may want to write this down in your notes. Um, if you have more than one mass that can be distinguished from each other. Like somehow you have maybe, yeah, a mass of one value and a different mass of a different value. But if all of those masses are sharing the same acceleration value, that's what we mean by a system. Let me just say that again. If more than one distinct mass share the same acceleration, that's what we mean by a system. Okay. And that's what we have right here. And just as a one big, if a system problem ever comes up again in your life or on the final or in the MCATs or something, my one thing to tell you about systems problems is that the trick of them is so again, put this in your notes and screenshot it and you can get points. When solving a system problem, the strategy is zoom all the way out first. That is, treat every piece that has the same acceleration, treat it all as one big attached thing, as many of you might automatically, right? And that means all system schemas, all free body diagrams, all force equations, all applications of F net equals MA, just look from the outside. Like in your mind, like for this, you would zoom all the way outside and you would draw a system schema of the combined M1 plus M2, like it's advising you to do. I'm saying this is a general strategy, right? So you would only then in the system schema or the free body diagram, you'd only draw forces that are acting on the combination M1, M2. Like like the table is touching both of them, gravity on both of them. What weight, what mg would you put for gravity? You'd put the total mg, like m1 plus m2 parentheses g, right? So first what you do is you just treat the whole thing as one item and do all solutions from that standpoint, thereby allowing you to get the acceleration of the whole thing. And then the strategy or the technique or the insight is whatever the acceleration of the whole thing is, must be the acceleration of every part, right? So you get the acceleration always. You get the acceleration of the whole thing first. You then you conclude or you infer, aha, this must be the acceleration of every part. They're all, in other words, they're all sharing that same acceleration value. They're all accelerating together. So that allows you to then drill down, zoom in Then you can, for example, do a system schema, a free body diagram, and a Newton's law application on M1 by itself, right? Or M2 by itself. And when you do that, then you include internal forces. In other words, once you zoom in to the block of M1, then you can count as a force, then you must count as a force the normal pressing in from M2. Do you see what I'm saying? And you'll be able to solve for that force now because you now have the acceleration of M1. So what I'm saying, and then I'm going to move on. I'm saying the way to solve system, the way to find out, the way to solve for the internal forces of a system is you first zoom all the way out and ignore all the internal interactions. Like first you just treat this whole thing as a blob. So if it's a blob, you don't, then it's not being affected by what's going inside. That's what we mean when we say net external force. When you draw a system schema of this whole blob, you do not count or include any interaction between M1 and M2. Just like if you were drawing a free body diagram of me walking down the street, the physics of me walking down the street, you don't count the fact that my spleen is pressing against my pancreas or whatever. And A, that's gross. And B, I don't even know biology, so I don't even know if that happens. But do you know what I'm saying? But then, oh, is there an attract? Oh, no. Then, so you zoom all the way out to get the acceleration of everything, but that's the acceleration of everything. So then you zoom in, and then when you zoom in, you count internal forces. You say, well, M2 is pushing on M1. And with what amount? Well, I can figure it out because I could do F net equals MA now on just the mass of M1. And what A do I plug in? The A that I already figured out from the whole thing. That's so one last way of saying it. First, you zoom out, and the M that you would analyze would be M1 plus M2. Then you zoom in, and you just analyze M1 or M2. That's the strategy for systems problems. That's what a lot of this is trying to get at. That's all I want to say about it right now. Get and like, okay, that's what I want to. But having said that, sorry. Having said that, I want to skip all the way down to the bottom and talk about what it's considering extra credit, but it's extra credit for this homework. I don't know what that means, extra credit, but as a capstone to this homework is now what launches us to the rest of the material and to the lab and everything. So at the end, you have this hand that's pushing with 10 newtons um, at, uh, at a 60-degree angle with the x-axis. So I just want to talk about that and how we deal with that and solve. So here, okay. So if that makes sense, I'm looking. Oh, chat. Sorry. Oh, good morning. Good morning. Excellent. Okay. Good to see you. Okay. So I'm gonna do the 60-degree, 10 Newton, and M1. Sorry, just and the total mass. I'm just remembering the number before I switch the eight. Okay, eight, 10. Okay, so we're switching the screens now. Do this every time. Okay, so as far as I'm concerned, this is the problem. Okay. So I've simplified the situation. I'm just distilling to the essence of it, which is that now we have this big block. Like I combined the two in my mind, like I was saying. So I have this big block of a total of 8 kilograms. It's on a table. Right now, the table is smooth. There's no friction. No, I mean, there's no roughness that's been mentioned. So the block is on a smooth table, and you're pushing the block with force P, like a push, but the push is at an angle 60 degrees below the horizontal, I believe is what the problem said. So you're pushing the block at an angle with 10 newtons of force. And the ultimate question, at least that I'm asking now, having distilled from the problem, is at what sorry, let me say one more thing. So you're pushing the block, but you're pushing it just because you're a human being and just because of like the leverage, the position is easier that way. But the block is on a table. So it's going to slide along the table horizontally. Just like if it were a sled and a child in the sled and you were pulling the sled, you might pull the sled at an angle, but that doesn't mean you pull the sled up into the air. Right? It still goes horizontally. So this block, so what we're solving for here is the acceleration of this block, which, just to be clear, is fully horizontal acceleration. That's the question: is given that mass and that push and that angle, what is the acceleration of this block? Or at least that is the question that I'm asking right now to quickly solve. Okay, again, I'm sort of just like distilling the essence of this last. So whether you did this part of the homework or not. So looking at the time. Also, wait, sorry. So hold on, let me just switch the view of the screen. Okay, so I'm gonna do the full procedure now. I'm gonna do it. I'm trying to do it a little more quickly. Just I think that's what people want at this point in the semester. Not quickly enough that you don't understand, but quickly enough to not waste your time. Should definitely put directly in the chat if I'm going still too slow or too fast, or if you missed something or whatever. It's okay. But okay, so I'm going to do the full procedure though, and a lot of these steps we've done a million times. So I'm just going to do them. I'm going to try not to over explain them. So here's right. I mean, in other words, this is step one. This is step two. Step three is always for all these kinds of problems. There could be other things to say too, but step three is definitely that. Now, step four is what someone asked me. Thank you very much. Someone got a lot of points for asking me and following up and making sure that I gave you this whole algorithm yesterday, Monday. Step four, like step 4A, is we're going to just quickly draw a system schema of the. So now we're in Newton's law problem. Every Newton's law, I would suggest that step four, you break into all these sub steps. Number one of which is a system schema, even though again we sort of already did it in the homework, but here's a system schema. Okay, the system schema is just that the Earth is pulling down on the block because it always is, and the table is pushing up on the block. Oh, and the person is pushing the block with their hand or something like that. So those are the three objects. A hand is pushing the block, the Earth is pulling the block, uh, and the table is pushing the block. And notice the fact that there are angles or directions totally irrelevant to the system schema. Those are just the objects interacting with the block. So then step 4B, I do a pure free body diagram. Sorry. Pure free body diagram. And it looks like this. We've got the weight of the block mg. We've got if that's the glitch you're talking about, I agree. Sorry. We've got the norm. Oh, the normal force up from the table And then we've got this person pushing down at an angle. So I go like that, P for push. I mean, technically that's a normal force too, but just to distinguish it from, okay, so those, right? So that's the free body, that's the pure free body diagram. We've got weight pulling down, we got normal force from the table pushing up. You might notice subtly that I don't assume that my normal force and my weight are equal in magnitude. I don't think they are. We're going to find out, but I don't think they are. Um, and then the push is down at that funny angle. It's just called push. So that's my pure free body diagram. Right. Actually, wait, let me make sure the chat. I'm going back and forth on my screens. Okay, everything's fine in the chat. Okay. So that's step 4B. Now step 4C. Now, so far we've done things like that before. But notice this is already this is the first time, at least in lecture, that we have a situation with like more than two forces. We have three forces now. That hasn't happened yet, I don't think. And now one of them is at an angle, right? An angle of 30. And I just, and you notice in the pure free body diagram, in the diagrams, I don't put numbers. I put names. In the system schema, it's names of objects that are creating the forces. And then in the free body diagram, it's symbolic expressions for those forces, but still no numbers. I'm not doing math. I'm setting up the math. So now in step 4C, this is now where we're going to make a component free body diagram. I kept alluding to this in Monday and perhaps last Wednesday, but I haven't done one yet for you with you. So let's do that. You could break these substeps down even further now. When I say component free body diagram, I mean that I'm going to that any I look at it and I go, wait, there's at least one force here that's not parallel or perpendicular to all the other forces. Like, P is off axis, assuming my coordinate system looks like this. Assuming these are my axes, P is not along them. Or, as you might recall from Lab 5, maybe my axes are like this. Like if you recall Galileo, which might also be another thing to write for step 3, one version of Galileo's principle. If you recall Galileo's principle, the laws of physics work when you look at the world this way, and they also work when you look at the world this way. They work the same way. As you may have now started noticing in the lab, sometimes this is more convenient, sometimes this is more convenient. You're allowed to make whatever choice you want, but you have to make a choice and stick with it. And you should make a choice that makes your life more convenient. So I'm saying all that to say, when I get now to component free body diagrams, honestly, the first sub step that you must do in order to create a component free body diagram, I'll say it's like step 4C1. You must consciously choose a coordinate system. I mean it. Just like in simpler problems, we choose what is like on the big or on the the Bowser Peaches thing that you'll get back soon. You had to like choose what is positive and what is negative on this axis and what's positive and what. That's Galileo setting up your frame of reference. Choosing your coordinate system is something you must do in physics. It's really where the action of physics is. So now I'm taking a step further and saying, you know what? You got to choose whether your coordinate system looks like this or looks like this. In the lab, you're choosing a coordinate system that looks like this because supposedly it actually makes it easier. It does. I mean, if you, we'll get to, but you got to choose. So, okay, here, and by the way, whichever choice we make, even if we go like this, then we got, well, I'm going to choose a coordinate system that looks like this. Choose a coordinate system. I'm choosing that my coordinate system looks like this. I'm choosing to line up the x-axis with the tabletop and the y-axis with gravity. I'm consciously saying the x-axis is the horizontal axis as opposed to being on an angle. And why am I doing that? Well, one simple reason is in this case, if I do that, I will. If I do that, then I say P is off axis. I'm going to have to break it up into components. And that is what I'm going to have to do. That's annoying. But if I chose this coordinate system, I'd have to break up two axes. I mean, then I would say, oh, gravity and the normal force are both off axis. So I'd have two sines and two cosines. You see what I'm see in the lab? The reason you go like this is because the situation is reversed in the lab. The in the lab 5, the object is not accelerating horizontally nor vertically. It's accelerating at an angle. So you look at the world this way in the lab. And so then you end up saying that gravity is off axis. You see what I'm saying? Which is very confusing to people at first. And honestly, most people just like they get annoyed, then they just accept it and they memorize it and they move on. Which is the wrong thing to do. I mean, well, it's better than other things to do, but um the reason you break up gravity in lab 5, the reason you break up a vertical line is because you're tacitly choosing that your coordinate system is not vertical and horizontal. It looks like this, right? Because the ball is actually sliding along an inclined plane. What that really, but here, that's not the case. So what I'm really saying now, and this is a thing what I'm saying is when you choose a coordinate system, always from here on in physics, you could choose whatever you want, but the laws will work the same. But you want to choose a coordinate system that makes problem solving as possible and convenient as possible. So the strategy is always the strategy. This is a huge point. I am going to try to resist the temptation to rabbit hole on this point and overtalk it. But please note if you're paying attention, like you might even want to write this in your notes and screenshot or whatever. Like this really matters in physics 204. I'm saying from here on in the strategy, when you think you need to break up some vectors, when you think it's possible that you're gonna have to break up some vectors, first, before you break anything up, choose your coordinate system so you know what's going to be broken up into what. People always think, I don't know which vector to break up. I'm not sure, like when things get complicated. People are like, I'm not sure if I should break up this vector or that one. And the answer is that's not the first question you should ask yourself. You should ask yourself, what is my coordinate system? And then you'll know what anything that's not along an X or Y axis is what has to be broken up. How do you choose a coordinate system? The big thing I'm saying, and then I'm going to move on, is always in physics as a strategy. You're not going to find this in a book because it's not a law, it's not a requirement, it's the strategy. You pick an x-axis, a positive x-axis that lines up with the expected positive direction of acceleration. If the ball in the lab is accelerating like this, you tilt your x-axis and line it up with that. If here in this case, even though the forces are all funny, in this case, the block is accelerating horizontally, like to the right. So your positive x-axis points to the right, okay? Like note that's a pro tip. That's 25 years of experience took me until I like really realized that's what was going on. Okay, so you do that. So you do that. So strategy, choose a. So then substep 2, substep 2. Now zoom in on any and all force vectors that do not lie along your axes. Like that's why you just did that. And you take those vectors and break up into axial components. Meaning in this case, so in this case, we're going to zoom in on that P, that push, right? That was at 60 degrees from the horizontal. So we're going to break it up. We're going to say something that's going down and to the right is something that's going down and to the right. But like we did with velocities and displacements on the first exam, which you'll get back. Another pro tip, right? Down right means down plus right in physics, but actually, it also means right plus down. And the pro tip is I always draw my horizontal first, and then from the tip of the horizontal, start the tail of the vertical and do that. So, right, if I'm pushing this thing like this, I'm saying what I'm really doing is to some extent going like this, and at the same time, but independently, I'm going like that. And I always draw my horizontal first so that in the end of the day, I end up saying things like southwest rather than west south, and or at the end of the day, my angle is always properly measured from the horizontal, and so that everything is consistent, self-consistent. So if P is going down at 60 degrees, then that means there's some component P cosine, which is adjacent to the angle, and this is SOHCAHTOA, right, in reverse, and then some component P sine theta that's opposite from the angle. So, and regardless of what the numbers are, really, so it doesn't even matter what the numbers are, this angle should be just called theta, right? This is what I mean by breaking up a vector, a force vector, right? Whether I knew the numbers or not, this is how I would do it. So then what do I do with this? So I've zoomed in, I've broken it, and if there were other vectors that were off axis, I would do it to them. So now I'm going to, what do I do with this? The purpose of that is now create a free body diagram. This is the component free diagram, the component free body diagram. In which all off-axis vectors, or I should say, are replaced by component pairs. Again, this is a trap that people fall into. What I'm gonna create my component free body diagram now, which is the thing I'm gonna use for the math. I'm going to create my component free body diagram. In the component free body diagram, every single one of those vectors that you just like broke up in a sidebar, you now replace with the two components that you just found. Every off-axis vector gets replaced with its pair of components. So that means you get rid of the off-axis vector. So you end up with something that looks like this. In this case, you'll end up with mg down, like mg was not off-axis, so I just leave it alone. And the normal was not off-axis, so I just leave it alone. It's there. But the p, what I'm really saying is down right. Not, I only want axial components now. So down right is not a thing, but down is a thing and right is a thing. So I replace. Right. So this is now my vector diagram. Notice the number of vectors has increased. It's increased, but notice the P is no longer in it. That's the whole point. I mean, people make this mistake I'm just saying, just don't make that mistake. Don't leave the P in the diagram. What we're saying is this is equivalent to the other diagram, only now it's ready for the math. Like that's a component free body diagram. You'll know you've drawn a component free body diagram if every single axis. Oh, sorry. And I see something in the chat, but I'll just finish the sentence. You'll know it's a proper component free body diagram if every single arrow in it is parallel or perpendicular to every other single arrow. Like things will only be on axes. Now the whole thing could be rotated, but as long, right, as it is in the lab, but lab 5. But everything is along an axis. So now we're going to do math. Now, someone in the chat is asking a very good question. I may have a hard time. The person in the chat is asking, how do we know what angle to select? I think I understand that. Well, I'm not sure if this is a good, I mean, in this case, they literally told you the angle. I mean, they said that I mean by theta here, what I mean is this theta, the theta measured between the force and the horizontal, the imaginary horizontal reference line. I picked that theta. Okay, I guess there's two reasons. One, because the problem specifically said it. Oh, another thing in the chat. Again, once I'm psyched, guys, good. But one, the problem specifically said it. I mean, it said, imagine that the push, I'm talking about the problem in the extra credit at the end of homework 7, where I got this from. It specifically said, imagine that the box is being pushed at 60 degrees below the horizontal. So that's reason number one. But reason number two is when in doubt, if there's any ambiguity, if there's any ambiguity in your mind about what angle to select, yes, my advice to everybody, my pro tip, if there's ambiguity in your mind, if the problem did not specifically make it clear somehow, then always try to measure, always err on the side of measuring your angles from a horizontal reference line. Measure your angles from horizontal as the basic habit. And then when you're breaking vectors up into components, always draw the horizontal first, and then from the tail of the horizontal, start the tip of the vertical. And there must be tips and tails. Sidebar, if this were on an exam or something like that, don't just draw triangles with sides. Like this is about vectors and directions. So the idea behind every right triangle, every vector triangle, is that a leg plus a leg equals a hypotenuse, like literally plus. And the way we plus in vector land, the way we add vectors is by putting them tip to tail. So what I'm saying is if you always draw the horizontal first and you always measure the angle from the horizontal, everything will be self-consistent, and that should be the answer to the direct chat person's question. If the problem didn't tell you something, reason to go and do something else. So I think that's the answer. Measure from the horizontal. But now I think, you might be asking that. I'm going to go on, and there's something else in the chat I'm going to go on to. But also, the person who just asked me that, please let me know if that sort of helped or not. But I'm even realizing why they might have asked that is for sure, this is a very subtle issue in Lab 5. Like what I'm trying to do today is giving you sort of all, even though I know, again, I know you already did the lab and stuff. That's the way it works. Like you play around in the, in the world and then you figure things out at home. Like welcome to physics. But like something that's, if you're doing the analysis of Lab 5 and preparing your reports, yeah, you have to do all this. You got to break up a bunch of vectors and you got to do this stuff. And this is the fundamentals. And then it gets applied in Lab 5 in sort of a difficult way, a challenging way. One of the challenges is, yeah, where is the angle in Lab 5? Well, even there, I'll say quickly, I'll try to get to it explicitly, but even there, the original angle that is given in Lab 5 is the angle between the inclined plane and the tabletop or the lab table. That, i.e., the original, the one angle in Lab 5 is the angle measured from the horizontal. Then the challenge is when then you go to break up gravity, for example, and you have to draw like a different triangle over here. Yes, your challenge is to see where in this sort of like vertical inverted triangle, which one of the two angles there is literally the same as the angle between the inclined plane and the horizontal. Like, yes, that's a challenging aspect. That may be why the person's asking. I'm not sure. A hint I'll just give you right now is that I just literally gave it away by like one of the two angles in your gravity triangle, one of the two angles is the same as the angle measured from the horizontal. The original. It's not immediately obvious when you just look which one to choose. But if you do geometry, if you stand back and like think about geometry, whether it's two parallel lines cut by a transversal, the alternate interior angles are congruent, whether you think about it that way, or there's ways to just draw the picture where you can eventually see either, and just ask yourself, if you really do this, if you made the inclined plane steeper and steeper and steeper, what would happen to that vertical looking gravity triangle that you're making? Like if you go like this to the plane, what would happen to that triangle? Which angle would increase? The one of them would increase and the other would decrease. If you think about it that way, you'll be able to figure it out. I mean, that's a lot, but that may be why. But yes, it's a challenge. Right now, I'm just giving the fundamentals. Okay, sorry. Yes, okay. And I will say more about that. I'm not trying to leave you in the dark. I'm just trying to stay on. But right, I'm with you. And thank you for the follow-up. Now, the other person in direct chat, can you draw the P? Oh, I see. So someone's asking in the chat, could I, in this diagram, could I draw? This is a very good question. I'm going to tell you right now. Well, okay, I'll just read it. The question is, can I draw the P sine theta vector as connected to the P cosine theta vector, like the way I did in the other diagram? In other words, could I have the P sine vector? Could I do something like this? Put the P sign there. Great question. I totally get it, but I'm going to say no. Like, at least for, I'm sure some websites do that and stuff. I'm not saying it's illegal. I don't, for me, please don't do that. I think it's an unhelpful habit in the long run. I think it confuses things. But because it's two different purposes, the pictures. One picture is to literally find out what P cosine theta and what P sine theta are, you know, that. But then here, what we're trying to do here is we're really trying to convince ourselves of and demonstrate all of the forces acting on the mass. Like what I really want to, I want to see in my picture. I mean, this is a technical, it's a subtle point, but if I draw it the way you're sort of asking, then it looks like the P is pushing on the P. But what I want to really see here before I set up the math is each one of these forces is literally acting on the mass. That is, I'm trying to get across now, and I'll move on. I mean, and if you don't like what I'm saying, I hear you. I mean, at some level, this is a style taste thing. But what I'm trying to get across is we did this work in order to then be able to believe or understand that we now have a block. We have a block that's being pulled down by the earth, that's being pushed up by a table, that's being pulled or pushed over by a hand, and that's being pushed down by a hand. Like, I really want to see that this block itself is actually being pulled or pushed in four distinct ways at the same time. I don't want to confuse myself and think it's being pulled in one way and then that, like, I really don't want to express that it's being pulled like this and then that pull is being pulled away. Like, it is being pulled four different ways at the same time. That's my, but I do get what you're saying. I think. But okay. So this is now. Now, what's the purpose of this? Now, so that was all like technically step 4C, the component free body diagram, C1, C2, C3. So now I can go to step 4D. Where I start applying F net equals MA to each axis independently. So I'll first go to the y-axis. Oh. F net, like now I'm applying F net equals MA. It's a vector equation. So the fact that it's a vector equation means it applies independently yet simultaneously to each of the axes. So I go one axis at a time. Pro tip, I always go to first the axis that I don't think I care about, i.e., we're ultimately solving for acceleration on the x-axis. Like, that's the ultimate question being asked here. What's the acceleration on the x-axis? So I always save that axis for last. Again, that is not a law. That is not a rule. Not all websites will say it, but that's a pro tip. You're going to do one axis at a time. Do the one that you're trying to solve for last, because you're going to very possibly get information that you need for that axis from the other axes. I'll leave it at so. So in this case, I do the y-axis first. So I literally now look, this is where I look at my picture and I'm like, oh, I look at all the y, this is plus, I mean, right, and this is plus, so this is minus, this is minus. So I look at the y-axis and I'm adding up all the forces. I have the normal is on the y-axis and weight is on the y-axis, only weight is pulling down in the opposite direction of normal, so it gets a minus sign. So I have n minus mg equals m, just like the duck yesterday or Monday, right? That's my statement on the y-axis. Now, in the y, and I solve everything I can on the y-axis. Do I know anything else on the y-axis? Yes, I do. What I will, in fact, always know, if I have lined up the x-axis to be along the same, great. Thank you, direct chat loop closer. Thank you. If I did my good strategy of lining the x-axis up with the expected direction of acceleration, then I know that on the other axis there is no acceleration. This is a subtle point again, but like on the like the block is not, the block is accelerating, but it's not accelerating up or down, so that is zero. And this is one of the reasons I always line up the axis. Why in the lab you line up the x-axis with the plane is so that you could say, so if that's the plane, then on the other axis perpendicular to it, the y-axis, there's no acceleration necessarily. Therefore, you can say that all the forces are balanced on the other axis, but you can only do that if you've chosen your axes correctly. Anyway, so here I can literally say, oh yeah, sorry. I can literally say n equals mg, like we said 2 days ago. In the lab, you won't get that, right? In the lab, you'll get that n equals mg cosine theta. Hint, 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 right? So, but it's by the same reasoning. Now, that's just a fact. I've just learned that n equals mg. Did anybody happen to ask that in this problem? No, actually, nobody happened to ask it. It's just a fact that I just learned, and it's as much as I can say from the y-axis. I'm going to move on to the x-axis, but please notice the reason. Well, here's. Basically, by going to the y-axis, I can learn something about the normal force, and it's different in different situations. It's particularly useful to learn what the normal force is if and when friction's involved, as you might have picked up from lab 5. If there's friction, I'm going to need the value of the normal force to figure out the friction. So that's another reason. So I do that, but there is no friction here, so I just move on to the x-axis. So now I say the sum of all the forces on the x-axis equal the acceleration on the x-axis. Oh, sorry. Oh, oh God. Oh my God. I totally, thank you, Nadine. Oh my God. Total points for Nadine. Wow. I'm contradicting my whole point of the whole exercise. Wow. No, Nadine is totally right. I just totally missed it. I'm going too fast. Back up for a second and please give yourself points for respectfully corrected, Nadine. Sorry. I mean, all the logic of what I'm saying is right, but whoa, 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 whoa. So sorry. Yeah, there's three forces on the y-axis. That's the whole point of this. Oh my God, I'm mortified. I'll never talk fast again. Right, the y-axis is actually normal force is up, gravity is down, and p sine theta is down. All that together. Thank you. I'm not going to dwell on it again, but if you missed that, if you just walked away and got a cup of coffee, there was a mistake. Well, we've changed it on the board. Yes, all the forces, and that's the purpose of the picture, is every single arrow that is along the y-axis should go into the y-axis equation. One last time. Thank you, Nadine. It is still the case. So that A equals 0, so that yes, right, here I then say, okay, then the normal force must equal mg plus p sine theta, which actually, right, I mean, it's so hilarious that I just accidentally left that out because that's really part of the purpose of what I'm trying to show you in this problem. If I follow this procedure, I'm still going to move on. But if I follow this procedure, I notice another example. This is kind of like the duck in the elevator thing, where the normal force does not equal just mg. Sometimes the normal force equals mg. Sometimes in lab 5, it equals mg cosine theta. Here, it equals mg plus p sine theta. The normal force is whatever it is. It differs from situation to situation. It's whatever it is to make F net equals MA be true, right? And so in English, what's happening, like, so if this block were on a scale, if it were on a scale while all of this was happening, the scale would register a number higher than its weight. Why? Because while this block is going along the table, it's being pushed by a hand. It's like literally being jammed into the scale more, right? Like, I mean, so Nadine is absolutely right. So what the table is supporting is more than the weight of the block. It's supporting the weight of the block plus this push that's jamming down. So the normal force does whatever the normal force does. The normal force is like its own little, it's a bunch of electrons acting like springs, really. So and so if there were friction involved in this problem, I would now need this expression for n to go on and put into the friction. But so far in this problem, there isn't any friction. So I go on to the x. So thank you again, Nadine. I'm going to stop saying that, but thank you. Um, so now I go to the x-axis. Um, and now we look at all the x forces there. And there's only one x force. There's only one x force there. And it is responsible for the acceleration. And that's what we're solving for. So this expression doesn't make any reference to friction or the normal force. So I'm just going to directly solve it. AX equals P cosine theta over M. And in this case, we have numbers for that. AX. P was 10, theta was 60, M was 8, right? So we have 5 over 8. So wait, is that what one put? Oh, 6.25, sorry. So suddenly didn't seem right. Okay. Okay, great questions in the chat. So that's the answer. So all of that is, and again, the big punchline of all that is exactly what Nadine noticed, and I almost didn't, or I didn't. That once you break up the diagonal line into components, then each of those components then figures into the F net equals ma equation, and presumably then affects the normal force. So that's how you deal with angles. Okay, then we still have 20 minutes. This would be a lot more interesting. Okay. Okay, so now I'm going to take the same problem and I'm going to add roughness to the problem and resolve. Okay, 18 minutes. So same situation, but now I'm going to say the table is rough. And I'm going to characterize the roughness of that table with two numbers, two coefficients. One is called the coefficient of static friction, and one is called the coefficient of kinetic friction, mu sub s and mu sub k. Whenever surfaces are rough, they are characterized by a roughness coefficient. And there's two different types of coefficients. One is called static, one is called kinetic. One is for the case with the kinetic. There's two different basic types of friction. Kinetic friction is the friction that acts when one surface is moving relative to the other. And static friction is a kind of friction that acts in order to prevent that. Static friction is a kind of friction that acts when you're trying to get one surface to move relative to the other, but it hasn't moved yet. Um, they both have the same basic, they both bear the same basic relation to the normal force. Okay. What in either case of well, let me one friction acts or the other for if surfaces are rough at all, either kinetic friction is acting or static friction is acting, but never neither and never both at the same time. And you should somehow make a note of that. But like, as long as surfaces are, if they're not rough, then they're not rough. If they're rough at all, then when you're trying to get them to move, it's static friction that's keeping them, holding them together. Once you get them to move, it's kinetic friction. Always one, never both, never neither. Now, what we said a couple of days ago is what friction is the parallel component of two surfaces pressing against each other. When two surfaces press, that we call that normal. And if the surfaces are rough, then the more you go like this, the harder it is to go like that, right? So friction is related to the normal force always necessarily, in that really they are just they are two perpendicular components of one phenomenon, which is stuff being pressed against other stuff, right? So there's a approximately linear relationship between the two. The more you press in newtons this way, the harder it is for them to slide in newtons that way. I mean, the more of this force there is, the more of that force there is. Okay, so it's like y equals mx plus b. X goes up, y goes up as a straight line. The slope of that line is what we call mu. The slope of that line is the roughness of the two objects. That is to say, the number of newtons of force you get this way per every 1 newton of force that you're applying this way, you get more of this action per every one of this action, the rougher the surfaces are, right? So mu is dimensionless number. It has no units. It's newtons divided by newtons. It's amount of friction newtons per every normal force newton. So it's just a pure number. And in fact, it's a pure fraction, usually between 1 and 0. If mu is 0, that means that surfaces are perfectly rough. Excuse me, perfectly smooth. If mu is 0, that means no matter how hard you press against them, you don't get any of this resistance. That's like an air hockey table or something. As mu gets, so the higher the mu, so mu is dimensionless. And higher mu means rougher. This is not legible, I know, but so like um glass would be like 0.2, and like rubber would be like 0.9. It's always a number between, it's just a coefficient of roughness between 0 and 1. So mu is not a force. It's a coefficient. You multiply that coefficient by the normal force, and that's what gives you the friction force. That's the base. So the basic idea is of friction in general. The fundamental relation is, in order to calculate the friction force, you take the coefficient and multiply it by the normal force. But there's this subtle thing of the two different cases. Literally, for the case of kinetic friction, it's exactly what you would want, what I would want. There's no twists or tricks with kinetic friction. Once one surface is moving relative to the other, if you want to know the friction force acting on it, and we'll do this example in a second, you take the coefficient of kinetic friction. In this case, it was given as 0.5 or 0.6 or 0.5. And as long as I know the normal force, I multiply the two together. That's the friction force. The normal force is on one axis, the friction force is on the other, right? Static friction is a little bit more subtle, a little more interesting. Static friction is not an equality like that. static friction will be precisely as strong as it needs to be so as to prevent motion or acceleration. In other words, static friction is whatever it needs to be to hold something still. If I'm pulling an object at 1 Newton of force, static friction will exert exactly 1 Newton of force to keep that object still. If I start pulling harder, static friction will pull harder. And oh, wait, sorry, there was a question in the oh, I'm a long time ago. Sorry, I don't know how I missed this. Can I repeat why I crossed it off and made it 0? I Sorry, that was a really long time ago. It may be wait. But I'm assuming that what I crossed off and made 0 was the acceleration. I'm assuming, and that's acceleration in the y-axis because the block was not moving up or down at all in the y-axis. Sorry, I totally missed that. And you could tell me again in the chat if you're still, but I think that's what you're talking about. Sorry. Static friction. If you pull, I mean, like this, the table, well, you can't see that, like my computer, like it's sitting there, right? I'm trying to pull it right now, but it's not moving. Why? Because something's holding it still. What? Static friction. Is static friction greater than my pull? No, because then the thing would go in the other way. So static friction is being exactly as hard as my pull right now. If I pull a little harder, static friction pulls a little harder. How does it do that? Electron repulsion. But at some point it can't anymore. It will pull exactly as hard, or push exactly as hard as it needs to hold always in life. That's what static like why things are basically okay, why everything is like sort of staying on my desk is because static even if a wind blows through my window, static friction will match the net external force on the object in that axis. It will do whatever it needs to do to perfectly equal the net external force attempting acceleration until it cannot. When can it not? When at mu s times the normal. So in other words, static friction is not equal. So therefore, so static friction is always less than or equal to mu s times the normal. Or put another way, if it's clear to you, you could say, in other words, Fs max, the most that static friction could ever be is mu s times the normal. So how does this all, so that's like the basics of friction. How does that translate to this example? In this example, we have the block on the table, the same block as before, but now we've been given facts about the table's roughness. So the first question is, what's the minimum force? Like, what's the minimum P for the block to accelerate? Like, in other words, how hard do I have to push on this block to overcome the maximum force of static friction? Well, let's figure it out. I'm going to cut to the chase. I would do all the procedures. So solving. This problem. Well, yeah. I've already drawn the system scheme. Well, now, okay. In the system schema, there would be one more line now. There's no more objects in the system schema. It's all the same objects. But that object, the table, now is connected to the mass in 2 ways. It's not only pushing up on the block, but it's also frictionally opposing it. So this is that case that I told you about last week, where we have one rough surface pushing against another rough surface. So there's 2 lines between those objects, one ultimately representing normal and one representing friction. So my system schema would get one more line. Then I go to the free body diagram, and the free body diagram has one more arrow, which is friction going to the left. And now to cut to the chase, because I'm trying, if I go to where this is going to matter in the math, if I go skip to the component free body diagram, the component free body diagram now is normal up, mg down, p cosine like this, p sine down like this, and now friction going back this way, friction opposing the motion. So there's a, right? So this is my component free body diagram now. So now, oh, thank you. Thank you, direct chat person with the, put that in, okay, thank you. With 4 minutes left. So now I'm now analyzing the friction. I'm going to do the exact same procedure as before. I'm going to say y-axis first, normal up minus mg down minus p sine theta down, all equals ma, right? So the normal force equals, and ma equals 0. This is the direct chat person's point. So normal equals mg plus p sine theta, right? Now, I don't know what P is yet. That's what I'm solving for. So I'm just going to leave that alone. But I now know an expression for the normal force. So then I go to the x-axis. And in the x-axis, I have P cosine theta to the right minus the friction to the left equals MAX, right? So now what do I do? And I know we only have 3 minutes left, but this is the key. So this was all the same problem as before, but now we have friction involved. So what do I do with friction? Well, here, so I substitute in mu times the normal. If in part A of this problem, they're asking me, what do I need to do to get the thing to move? I would substitute mu s times the normal. When I get to part B, if I don't get to that today, if I get to part B, and they're asking once it's moving, what's happening? Then I would substitute mu k times the normal. Here I'm doing part A. So I go P cosine theta minus mu s times the normal equals MA. And in order for it to move, it's going to have, well, equals MA, right? So I'll just repeat that. So I have P cosine theta minus mu s times the normal equals MAX. Now, what's the normal? It's what I got from here. And that's why I always do it this way. And this is what you're doing in the lab too. It's just that the y-axis is like that. But this is the procedure in the lab. So I sub in from x-axis. So I say P cosine theta minus mu mg plus P sine theta equals MAX, right? So it's getting complicated. 2 minutes left. And the question here is, what's the minimum we need to push so that the thing moves at all? So in other words, we need this, we're looking for the minimum. The minimum, that means it has to be anything to make the acceleration anything greater than 0, right? We're just trying to get it to move. So I can say P min cosine minus mu s mg minus P sine theta, all, is all equal to 0, anything greater than 0. There's 1 minute left. There's no minutes left. There's 1 minute left. But luckily we're like, there's one more line and then we're there. Oh my God. So I'll just start on the next page. So we have P min cosine theta minus mu SMG minus P Okay, we're just 1040. And so what do? I'm solving for P here. So I'll leave all the P terms together and bring the mu S mg to the other side. Sorry. To the other side. And then factor out a P and divide. So P, or factor out P min. So I get literally I'm going to leave it at part A. We won't, I'll start, but this, and then plug in the numbers. And that's the answer. Now, it's okay. So just plug in the numbers and that's your answer. Bottom line, takeaway, is it starting to look complicated now? Yes. Is that as complicated as the lab? Yes. Is it the same thing as the lab? No. But the lab and this are just applications of this. This is the procedure. This is how things work. Okay, you've been very patient. It's 1041. I will sit here for a second and plug in the numbers so you can have an actual answer if that's satisfying, and you can wait if you. But if you've been that, so I'll put in the PDF. So I'm going to turn off the recording. I'm just going to. I might even right now put an answer for part B too, so you have it in the PDF. In fact, I will. And if you want to stick around, but go. Have a nice. Hopefully, this is helpful. Okay, bye, bye, bye.
Thank you so much.
Thank you so much. Thank you. Okay. So I'm stopping the recording.